Start, yeah.
So, good morning, everyone. Today, on the last day of the Limit Camp, we are a pleasure to invite Professor Niranjan Balachandran from the Department of Mathematics at IIT Bombay. Professor Balachandran is an alumnus of Indian Statistical Institute, having completed his bachelor's and master's in statistics from ISI. Following his time at ISI, he earned his PhD in mathematics from Ohio State University and served as an instructor at Caltech before joining as a faculty at IIT Bombay. His research primarily focuses on combinatorics, especially in extremal and probabilistic combinatorics. Today, he will be giving a talk on the regularity lemma. So please join in welcoming Professor Niranjan Balachandran for the talk. Over to you, sir.
Thanks, Shubhajit, and I suppose thank you all for coming. First, let me share my screen, and you tell me if you can see. Can you see the screen?
Yes, sir, it is visible.
All right.
Yes, sir.
Okay. So, all right. Is there any? So, in case, so first thing that I want to say is, in case anybody has any questions or anything, please feel free to stop me. I want to do one thing. So, first of all, let me get a very brief idea about the background of all you guys. So, you're around 10 of you here, I suppose, right? What are you guys doing right now? Before I start talking anything mathematical, I just want also to get to know a little about my audience. Since there are not too many of us here, we can indulge in this small exercise. So, yeah, please, each of you among the audience, just tell me what you're doing.
Hello, sir. Am I audible?
Yeah.
So, sir, actually, I have moved to second year. I am currently in IIT Kharagpur, and now currently I am working on number theory and discrete mathematics.
So you're in the math department there, or which department in IIT Kharagpur?
No. Actually, I am in the agricultural and food engineering department, but I have applied for a double major in mathematics and computing.
Okay. All right. Very good. Thanks. Very nice. Next, Arham.
Yeah, I'm going to second year now at VIT Vellore doing computer science.
Okay, excellent. Shubhra. And I'm just calling out the names as I see here on this list. Yeah, please. Yeah.
Yes, I am Nilimesh Kole. I am student of in class 12.
Okay, very good. Let me see in my list. Okay, what about Avradeep?
Sir, I'm currently in 12th this year.
Okay, excellent. Harish? Harish, can you hear us? Because we can't hear you. Okay, yes. No, you're not audible. But if you want to type your message, you can do so. I'll go to the next person in the meanwhile. Rohin?
Sir, I am currently pursuing my bachelor's at Ramakrishna Mission Vidya.
Okay, excellent.
I'm in second year.
Okay, and Shojato?
Yes, I am also a student of Ramakrishna Mission Vidya Mandira, and I am just completed my second year in BSc.
Okay, excellent. So Harish has said he's pursuing BTech in mathematics and computing from IIT Dhanbad. All right. So have we left anybody out? Completed second year again. Swayanshu.
Sir, I am currently studying in class 12th.
Okay, all right. So have I missed anybody? If I've missed anybody, you can just let me know. Okay, so if we haven't missed, this is fine. This is a reasonably good enough bunch of people. So let me also start this. You can maybe show of hands or whatever. Of course, virtual show of hands. How many of you have heard of this thing called a regularity lemma? Because I want to know how informed or how much my audience knows before I can launch into this. So if anybody knows, you can just show your hand or raise your hand, or sort of typing, that would be easier. Okay, I don't see anything go up. So may I then conclude that you haven't really, even if you've heard of it, you really don't know what this regularity lemma is, what it is about also. Am I correct? All right. Okay. So let's start with this. Now, the regularity lemma is actually a very deep statement in graph theory. Now, what do I mean by a very deep statement? You see, think of it this way. Supposing a statement is true about all human beings. Either you're saying something very trivial, like you're saying, well, all human beings who are alive have a pulse. This is almost tautologically equivalent to the definition of having life. So, if I tell you a statement which must be true of all human beings, either I am telling you a very trivial statement or I am telling you a very deep statement. The same is true about almost any category of object. If some statement is universally true, it must be either a trivial statement or it must be a very deep statement. Now, when you come to a very deep statement, which the regularity lemma is, one of the main points about the regularity lemma is I will start out with some history about the regularity lemma, what it is and so on. And as I put in the title, what it is and how it was possibly discovered. See, the regularity lemma is the work of Andre Szemeredi in the early 70s. And the statement of the lemma itself is not very difficult. So it is an outrageous statement in some sense. And one of the hardest spots of the regularity lemma is the two things is how does one conceive of the regularity lemma? How does one think about it? Or you can ask, how the hell did that man come up with this statement in the first place? So what I will do here is in some sense called trying to solve an exposition problem. Now, this is best encapsulated by the words of Tim Gower. So I'm just going to tell you what he writes. See, Gower says solving an open exposition problem means explaining a mathematical subject in a way that renders it totally perspicuous, which means every step should be motivated and clear, and ideally students should feel that they could have arrived at the results themselves. Now, what I am going to do now is try to present the regularity lemma from this point of view. So I want you to keep this at the back of your minds, because this is my stated objective. What I want to do is to bring forth the statement of the regularity lemma, first make its proposal and then its proof and so on. Let's see how much we can get done by 1 o'clock, or maybe if it goes a little over. But since my objective is that you people should have been able to arrive at this yourselves, if at any point during the talk, something that I'm saying doesn't sound clear or it sounds vague or whatever, feel absolutely free in stopping me and asking me for clarification on this point. Okay, all right. So before I go to the regularity lemma, let me start with some historical results. Now, one of the first statements which set off a whole series of results in motion actually is what is called the Hilbert's irreducibility theorem, which is nearly 130 years or so. What exactly is the statement of the irreducibility theorem? This is something that all of you should be able to understand. So first of all, let me ask this question about notation. Is this, everybody knows what this is, right? This is all polynomials in the variables x and y. Okay. So just so we know, this is with integer coefficients. So there are two variables, and these are all polynomials in integer coefficients. Now, what exactly does it mean to say it is irreducible or reducible? Whether irreducible or reducible means it can be written as a product. So if it is reducible, f is irreducible. F is reducible if it can be written as g times h, where both g and h are not 1. I mean, and both are themselves polynomials with integer coefficients. Okay, definition makes sense. All right, and now what exactly is the statement of what was the statement of the Hilbert irreducibility theorem? It says, supposing you start with a polynomial in two variables and it is known to be irreducible, or let me start with the contrapositive. Supposing you know that the polynomial, so one thing you can do is you can plug in y equals t for various real numbers, for various integers t. Okay, if you plug in y equals t, this will become a polynomial in only one variable, namely x. Now, when it is polynomial in one variable, presumably you can try to see if you can factor it into other polynomials and so on. By the way, at this point, I must make this clear. Fx equals 2x. Is this reducible or irreducible? If I look at it at polynomials over the integers, let's just start with a simple example. Or let me make it even better. 2x squared plus 2x squared plus 4. Do you think this polynomial is reducible or irreducible? Any answers?
Reducible.
And why so?
2 times x square plus 2.
Yeah,
So
that's
2
the
is a
point.
polynomial.
See, even though the polynomial x squared plus 2 has no, so because even though x squared plus 2 is as such, x squared plus 2 does not, you cannot factor it over the rationals, but the point is, the definition here says that neither of them should be one, should be a unit in the ring, in this particular ring of polynomials. So anyway, Hilbert's irreducibility theorem states the following. Supposing you use, so basically it says that there is a t naught, there's an integer t naught such that whenever you start plugging in t for t greater than t naught and the resulting one variable polynomial is reducible, then the two variable polynomial is also reducible. Or if you want to put it in terms of irreducibility, the best way to understand this statement is if f is an irreducible polynomial in the variables x and t, then it is possible to find infinitely many values of t, such that if you plug y equals t, you get an irreducible polynomial in the variable x. Does it make sense? Yeah. Okay. Now, at this point, one of the things Hilbert does in the proof, and now I can't tell you about the proof. But those who are interested, there's a very beautiful article about this in the American Math Monthly. I can try to dig up the exact link and send it to Shubhojit if there are any interested people. I can even forward the article. But I think it should be accessible to all of you. It's not unreadable. But here is the interesting thing. In the proof, Hilbert basically proves a very combinatorial statement in between. I mean, and here is the statement that he proves. So, given integers r and k, there exists an integer h, which depends only on r and k, such that the following holds. You see, for any r coloring of the set, what is an r coloring? So, it is just a partition of this into at most r sets. Or another way, if you want to write it in a more colloquial or easy to understand language, it would just be that if you take each of the numbers 1 to h, think of it as you're going to color it using one of r colors. Supposing r is 3. So each of these gets a color 1, 2, or 3. Okay. So what the statement says is, given r and k, there is a capital H which depends only on r and k, such that no matter how you r color the set 1 to h, there is a monochromatic k cube, that is a set of this particular type. See, why is this called a k cube? And let me make this maybe more clear. Imagine, so this is almost, so why is it called a k cube? Here is the reason. For example, this is our usual square, that is 2-dimensional cube. This is the 3-dimensional cube. And then you can, a 4-dimensional cube will be, you have to join appropriately the corresponding things and so on. So this will be a 4D cube, for example. Okay. Now, what exactly you're saying? Epsilon i's are zeros and on. So if you want to put coordinates, let's just start with this. Yeah, in 3 dimensions. Or let me start with just the 2-dimensional case. This is 0, 0, 1, 0, 0, 1, 1, 1. Yeah. So if you take the cube in 3 dimensions, its coordinates will be 0, 0, 0, 0, 0, 1, all the way till 1, 1, 1. Yeah. So in particular, the k-dimensional cube, the coordinates will be a k tuple where each of the entries is either 0 or 1. So if you think about this, these ai, so each of the epsilon i's are here. So if you think of epsilon as epsilon 1, epsilon 2, epsilon k. Now, as you vary this over all possible k tuples, sorry, all possible 0, 1 tuples, this looks like the k-dimensional cube. So in some sense, this is called the cube lemma because it looks like there is a cube and there is a certain way to project that cube down onto the integers. And what all points that you get from this in the process, all of those will end up being points of the same color. Okay. Does the statement make sense?
Yes.
All right, good. Now, let me now go over to see, once this statement of Hilbert was proved, it's part of his irreducibility theorem. In about roughly around 25 or 30 years later, van der Waarden proved the following statement. And this is a slightly recreational version of the same thing, but you can think of it, Ben, let me just tell you the statement. It is here. Given integers r and k, there exists an integer w, which depends only on r and k, such that, so this again is a notation for when I said square bracket a number, this is all numbers from 1 to w. Okay. So you take any oops. You look at any k, you look at any r and k, and you look at the integers 1 to w, then there is, no matter how you r color those integers, you can find a monochromatic arithmetic progression of length k. All right, now this statement is interesting, intriguing in its own way, and it is by no means a very easy statement. It is quite a complicated. The original proof of van der Waarden is a very clever double induction on r and k, and it is not that straightforward. If you want to see it, it can be seen. It's not beyond what you can learn, but it's not an entirely trivial or straightforward statement. Now, one of the things that Paul Erdős and Paul Turan, they did was the following. You see, let's go back to the van der Waarden theorem. Supposing you have the integers 1 to w, all right, and I color them using r colors. Now, by the pigeonhole, one of the color classes will have at least 1 by r many points of the total set, right? So in some sense, it is not an unreasonable thing to expect that the color class in which there are most number of elements, probably that is the one in which there will be such an arithmetic progression. Did that make sense? The most popular color class, which is to say the color class with the most number of points in it, it's a reasonably good expectation you can have that in that color class maybe you can find the arithmetic progression you want to find. So that was exactly the statement that was the conjecture of Erdős and Turan, which goes the following way. You give any epsilon between 0 and 1 and take any integer k at least 2. There exists an n naught which depends only on epsilon and k, such that if n is at least as large, so for all large n, you take any subset a of 1 to n, such that size of a is at least epsilon n. So in other words, if you take any set whose set size is non-trivial in that sense. What do I mean by non-trivial? Here is all I mean by non-trivial is to say that this set size is somewhat large. Okay. Now, when you have any such set size, they conjectured that such a set must already contain a k-term arithmetic progression. Now, you see, of course, if the Erdős-Thurán theorem is true, then van der Waals will follow easily, because you take epsilon to be 1 by r. You're coloring it to r in r color classes. So at least one of the color classes will have 1 by r and many points. So for epsilon equals 1 by r, the Erdős-Thurán conjecture will tell you exactly the van der Waals theorem. Okay, any questions so far? No? All right. Now, the conjecture was made in sometime in the mid-30s, and of course, because it seemed a very naturally interesting statement, because you see, it is a purely combinatorial statement. It doesn't require you to know anything else to be able to understand what the statement is saying. So, of course, it generated a lot of interest, and people were trying to attempt to solve it. So, the case k equals 2 is trivial, because what is a two-term arithmetic progression? Any two distinct elements are already a two-term arithmetic progression. See, to talk about a k-term arithmetic progression, yeah, I would say that you have x1, x2, xk is a k-term arithmetic progression. If I have, you see, x1, x2, xk is a k-term arithmetic progression if and only if this is true, right? For some d, these all must be strictly, these consecutive differences must be equal. Yeah. And so if k equals 2, you're not saying anything. I mean, you're saying x2 minus x1 is non-zero. So any two distinct terms you have in that set, that is already a two-term arithmetic progression. So only for k equals 3 does the statement start to become non-trivial. And for k equals 3, already it is non-trivial. And so it was then a result due to Klaus Roth in 1953, that this conjecture was proved for k equals 3. Again, what does it mean to say? It means the following: for any epsilon, as long as size of A is at least epsilon n, there will be a 3-term arithmetic progression sitting inside A. All right? Is the statement clear?
Oh, yes, sir.
All right. Now, first, I'll tell you two interesting things. Klaus Roth was a Fields medalist, I think, in 1952 or in 1956. I forget in which year. And one of the citations for his Fields medal winning was actually the solution of this problem. And what he did, I mean, his solution uses Fourier analysis. Now, again, are you somewhat familiar with what it is? Do you know what Fourier analysis is? Supposing you don't know, it doesn't matter. It's an old technique. It goes back to Joseph Fourier. It's a very powerful analytic technique, and the proof works very beautifully for k equals 3, but it is not at all clear how to extend it from k equals 3 to k equals 4. Forget all general k. And it doesn't generally easily extend because, well, Tim Gowers later managed to find some way of extension, which is what led to his Fields Medal citation when he won the Fields Medal in 98 for kind of extending that, for generalizing those Fourier analytic methods to the more general case. So what I'm saying is the problem is hard enough that well, there were two Fields medalists just trying to solve it in two different cases. But Gowers did not solve this problem. The problem was solved by André Szemeredi. Now, Szemeredi solved this in 1974, roughly around 20 years after Roth did it. First, Szemeredi proved the case for k equals 4. And then shortly afterwards, I think he realized that the proof extends for all k. And he proved it. He gave the general proof for all k. Now, to tell you the proof of Szemeredi is extremely complicated. What do I mean by that? I will show you one page from Szemeredi's paper, which proves the Ardèche-Thoron conjecture. All of you see this flowchart here? Yeah, is this flowchart visible to everybody?
Yes, sir, it is visible.
Okay.
Yes.
Now, what do you think in this flowchart? There are some circles labeled with some letters. There's F1, F2, F3, L1, LT prime, L4, F9, then F0, D, and then C, T. There are all these things. Actually, these Fi are Fk is fact number K in the paper. Lk is lemma number K in the paper. T is the theorem. C is the corollary. And so this flowchart, because there are so many statements and lemmas and other things in the paper, it is not even clear to somebody who's reading the paper, who has even understood all these lemmas and facts and statements, that the theorem has actually been proved. So Szemeredi actually had to put in a flowchart to explain how, even once you've proved all these things, actually you've proven the theorem. You understand what I'm saying? There are lots of lemmas and facts and propositions and other things that appear in the paper. For somebody who's just seeing the statements of all these, it is not even clear that from all these statements, actually the statement of the theorem has been proved. So, in fact, he had to include a flowchart to convince the reader that, oh, if all these statements are true, then actually I have proved the statement. So, in some sense, even though Szemeredi proved this in 1974, there were always attempts to try to understand the proof better, and it has led to a lot of other very interesting mathematics, very new techniques, and so on. But I'm not going into that. I just put this particular slide to try to emphasize to you that the proof is a very complicated proof. Okay. Now,
What is the circle denoting, like, for the facts?
Which one?
The circle that is there in F4, F6, F7, F8,
This-
F0. Yeah.
This
What is
particular
the
circle. No, these all appear like a completely disconnected set of facts. The point is, the van der Waals theorem, it implies this. But these statements, they have some equivalences, and then there is an equivalence between this Tm and this body of facts.
Okay,
so,
like if we assume this, what these facts are assuming in union, and then that would be implied.
yeah.
To
If
Tm.
at least one of these is true, then that is equivalent to Tm.
Okay, yeah.
In that sense. So you see, that is why, in fact, it makes the theorem that much hard to prove, hard to understand that the proof is actually done. See, the T is the main theorem you want. Ardèche-Thoron. Van der Waals was known because Van der Waals actually had an induction proof, which is not, as I said, too hard to understand, but it is. Anyway, I don't want to step too much into this particular statement, because if I go there, I will spend up more time talking about this and not about the regularity lemma, which is the topic of interest for my talk today. See, why did I get into all this? Because, well, the regularity lemma is a tool that was introduced in that proof. And of course, it appears as a lemma. And because it appears as a lemma, see, usually, and all of you you've done some mathematics, then you all know that lemmas are sort of technical statements that are in between. They are not standalone results. Theorems are standalone results. Lemmas are technical statements that you write in the middle of a proof. Okay, so in that sense, this appears as a lemma. But so it has become very popular. I mean, Szemeredi called it the regularity lemma, and so it is known as Szemeredi's regularity lemma, or sometimes simply as the regularity lemma. But it is important enough to merit special status, which is why I'm going to talk about it. I just said a few words about it. See, this regularity lemma is more than just a lemma. It is actually a philosophical statement. And it has, after that, the regularity lemma has had many generalizations. I'm just throwing some words here, not that they probably mean anything to you guys right now, or even if they don't mean, it doesn't matter. I will share these slides with Shubhajit, so that if you want, you can look at these later for your for going through or perusal at your leisure. But the point is that the regularity lemma has lent itself to lots of other generalizations, and it has very strong applications in other areas, including in theory computer science. So I will not talk about all these various versions. For me, the regularity lemma will be to the very basic version, which is for what is called dense graphs. What are dense graphs? Well, a graph is dense. Let me say this. A graph is dense if see dense when I say this is not responding very quickly. When I say a graph is dense, it means that the number of edges is quadratic with the number of vertices. Does it make sense? So I say a graph is dense if the number of edges in the graph is some c times n square.
Yeah.
Okay, for some c. Now c could be very, very small. I mean, c could be 0.000000, and you put 10 zeros and 1. The point is that it is an absolute constant. So dense is in that sense. The number of edges is actually quadratic. Okay, keep that in mind. So even for this, the result is not going to be very straightforward or whatever. So whatever I'm going to do is I'm just going to work on this. Any questions so far? All right. Let's moving on. The more important thing, as I said, is Szemeredi's proof is purely combinatorial. He did not use any analytic tools like Roth's proof, for example, did, or Gower's proof later does. So I will try to show you Roth's theorem. So what exactly was Roth's theorem? I'm going to give you a combinatorial setup. So let me. I kept this so that I can. So what is the statement? You're given the following statement. That A is, so you, oops. You're given a set A. Having a little trouble with this is not responding very quickly, but all right. So here you are given a set A. Size of A is, say, epsilon n. Now, of course, I am now going to assume that epsilon is rational, and instead of putting floors and ceilings, let's ignore those for the time being. It doesn't really matter. So I'm going to write A, size of A is epsilon n. Now, what I want to do is what is Roth's theorem? You want to show A has a 3AP, 3-term arithmetic progression. Okay. Now, here is a very nice graph theoretic way of doing it. So you take 3 sets. You take the set 1 to n, call this set X. I'll take 3 sets of vertices. All of you are familiar with some basic graph theory, correct? Yes?
Yes, so they are raising up their hands.
Okay, good. So now do you understand my notation here? This is the set. This is basically the integers 1, 2, ... n. This is like 1, 2 till 2n. And this is 1, 2 till 3n. Okay. Now, what I'm going to do here is, let me put, okay, you put an edge between some vertex X and some vertex Y here. Okay. If Y minus X is in the set A. Okay. Now, similarly, I'm going to put an edge here. If Z minus Y is also in the set A. Okay. And finally, I will put an edge, say, between two vertices here. If Z minus X is in 2 times A, this is all which are multiples of, I mean, any element of A times 2. That's what this notation is. 2 times A is all 2A such that A is in A. Okay. Does that make sense? Now, by the very picture that I have drawn, what does it say? Supposing you have a triangle here like you have. That means Y minus X must be some A, right? Z minus Y must be some B, and Z minus X must be some 2 times C for A, B, and C in the set A. Correct? But you add up these two, what do you get? Z minus X plus Z, Y minus X plus Z minus Y, Z minus X. So that tells you A plus B is 2C. This will tell you A plus B is 2C, which is the same as saying A, C, B is an arithmetic progression. Make sense?
Yes, sir.
Okay. Right? Okay. So what have we done by this small little gadget? Well, how many vertices are there in this graph? There are n plus 2n plus 6n vertices. Okay. Let's also count how many edges are there in this graph. What is the number of vertices of this? Let me call this graph a name. I'll call it gamma. Okay. This graph is gamma. Let me just say this is this graph here. I'm just going to call it gamma. The number of vertices of gamma is 6n. And how many edges are there in gamma? Let's try to compute that also. Now, between X and Y, now I'm not going to put any edges inside X, any edges inside Y, or any edges inside X. All edges are only across. Now, between X and Y, how many edges are there? Between the sets X and Y, how many edges are there? Pick any X here. Take any element little a in capital A. Then X plus little a will be a neighbor of X in Y, correct?
Yes, sir.
So each number, the number of neighbors, so if I write this as this, I want to say, is basically size of A times N. Okay. Similarly, this term, second term here, is size of Y. Maybe I'll write the same size of X times size of A. And this will be again size of X times size of A. Well, just put 2 times, you will add. So this actually, if you see, size of A is like epsilon n, X is n. So this basically will be some constant. Well, that depends on epsilon, but n square. Yeah. Let's C is a constant depending on epsilon. I mean, I can be more exact. I just don't want to do it because it's not going to serve any big purpose. But any questions so far? Right? All right. So what this then does for us is, so as I wrote, if G has a triangle XYZ, then it tells you that Z minus X is A, Z minus Y is B, and Z minus X is 2C. That tells you a 3-term arithmetic progression. Except there is one small problem. Does anybody spot the problem? See, what have we done so far? We wanted to find a 3-term arithmetic progression. I've converted that into finding a triangle in a certain graph. Okay. So I'm saying if there is a triangle, if there is a three-term arithmetic progression, there is a triangle. Is the converse true? If there is a triangle, does it mean you have a three-term arithmetic progression? See, three-term arithmetic progression means those three terms must be distinct, no? In this setup, what says that A, B, C are distinct? They may all be the same. If A equals B equals C, of course, A plus C is 2B. But it will not give you a three-term arithmetic progression. So that is what is called a trivial arithmetic progression. So as I said, not all triangles are proper arithmetic progressions. If A and B and C are same, then x plus A, x plus 2A will be a triangle, but it is for our purposes, a useless triangle. So the point is, you throw away all these useless triangles. If there is a useful triangle, then you're in good shape. Does that make sense?
So we basically are trying to delete those triangles or something to obtain non-trivial triangles?
Well, you can do, if you can delete it if you wish, or you can think of it from another point of view. Let's see, how many useless triangles are there? Since you brought up this question, very good. Let's ask this question again. How many useless triangles are there? You pick any x, okay? Any x in capital X, any A in capital A, then it gets you such a triple, correct? These are the only really useless triangles, because any such triangle will give you a trivial arithmetic progression, which with common difference 0. How many such choices are there? The size of cardinality of x. What is the cardinality of x here? Cardinality of x is n. Oops. Yeah, these are, I think, occupational hazards with these things. Okay, so size of x is n. Size of A is epsilon n. So number of useless triangles is so for example, instead of saying deleting, which is what you were asking, if you know that there are more than epsilon n square triangles, all right, then you must have a non-trivial triangle which will help us. Make sense? But
I couldn't understand.
Sorry?
From the trivial case, how do we arrive at the non-trivial one?
No. So if you remove all the trivial triangles, that the total number of trivial triangles is epsilon n square. So if the total number of triangles is strictly greater than epsilon n square, there must be a non-trivial triangle.
Yeah.
That will tell you your three-term arithmetic progression. Okay. See, so far, whatever I'm saying to you, I hope I have not used any extra language. I'm not using any extra terminology. I'm writing it in terms of things that you all can intuitively understand. Correct?
Yes.
Yes. Okay, good. All right. See, here's another point. I am not seeing you. So if you nod your heads, it doesn't help me, because all your videos are off anyway. I'm not going to keep checking your videos. So you can, unless there's background noise where you're sitting, if you want, you can keep your mics on. I don't care. There are only 10 of you. But if I get feedback from you, that helps me. Yeah. So Swayam has a question. Why to remove trivial triangles as we want AP and it is an AP in difference 0? Well, what do I mean by remove? You see, as I'm saying, a trivial triangle will not count for us. You want to show the existence of a non-trivial triangle. So a non-trivial triangle is equivalent to saying there is a non-trivial three-term arithmetic progression, correct? So once you have that particular perspective, you just want to count the total number of triangles in the graph. All right. Now, so as I said, one possible way to show that there is a non-trivial triangle is you count and say how many are there, many triangles. Now, there is one graph theoretic. So you can ask the following question. How many three-term arithmetic progressions are there in such a set? Now, before I come to that, I want to make one other important point here, which is, you see, even so, this is an important fact to be beware of. So I'll write this as something to, beware of. It's not a, I mean, those who know this before, you have seen this thing before, it's good for you. Otherwise, it doesn't matter. The fact is, you can have a graph with lots of edges and still no triangles. Yeah. See, in fact, if you take a bipartite graph with, say, n/2 vertices on each part, yeah. So since the pen is not really working very quickly, I'll just say this. Just because a graph has many edges doesn't mean it has even one triangle. You can have quadratic number of edges and have no triangle at all. So even though we are framing it in this fashion, and we only know that the number of edges, see, we looked at the number of edges in something before, and we saw that there must be, so there are graphs. So you can have a graph whose number of edges is as large as n square by 4 and still no triangles. All right. So first of all, having many triangles, having even a single triangle is not guaranteed just because the number of edges is quadratic. But let's keep that in mind. Now, here's another question, which is, okay, how many, supposing you think that there is at least one three-term arithmetic progression, is it possible that there is only one, or can there be many? Now, this was a result shortly. So remember, Roth proved his theorem in 1952 actually. It appeared in 1953. So but I think 1950-51 it was already proved. Varnavides in 1959 showed the following sort of generalization, which is to say, see, as long as the set, supposing the set has size at least epsilon n, yeah, then the number of three-term arithmetic progressions is quadratic in it. It's not as if the number of three-term arithmetic progressions can, if it is not 0, it can be only 2 or 3 or 100 or something, depending on n. So given an epsilon, there exists a delta, which depends only on epsilon, which says with the following statement: if size of A is at least epsilon n, then the number of three-term arithmetic progressions will be at least delta n square. So the number of triangles, the number of three-term arithmetic progressions will blow up to be quadratic in n. Now, as I said, I've written this statement. I won't write it quickly. It's actually a very simple back calculation, because for every arithmetic progression you get, you start with an x. You start with the three-term arithmetic progression. You will get x plus a and y plus b. That will already give you another triangle in the graph. So the number of triangles then turns out to be cubic in the graph. That is, if it were true, what you want to then be able to show is that this particular graph should have cubic many number of triangles. That's one thing that you can hope to do. Am I making sense?
Yes, sir.
Yeah. See, again, if any question that anybody has, see, I'm spending a lot of time just trying to arrive at the statement. So it is possible that I won't have time to show you all the proof and so on. I don't care. But what I want you people to take away is at least understand where the statement of the theorem is coming from. Okay? All right. So
just Somanshu has a doubt in the theorem statement.
yeah. Yeah, go on.
He puts it in the chat.
Swanshu says, couldn't understand. Couldn't understand what is delta. See, delta is just an absolute constant. So like how you see epsilon delta statements in calculus, this is a similar kind of statement. See, so if epsilon is maybe 0.01, delta may be 0.000001. The point is, it is another constant which depends only on epsilon. All right. Sir, how n cube is coming? Well, it go to understand why n cube is coming, you just have to go back to this. As I said, every time you start with any element in X, you start with a 3-term arithmetic progression. You pick any X, then X plus, so Y will be X plus B, Y will be X plus A, and Z will be Y plus B. That is X plus A plus B. That will be a 3-term arithmetic progression. So pick a 3-term arithmetic progression, pick an X. The number of arithmetic progressions is quadratic in N. The number of choices for X is linear in N. So total number will be cubic. Does it make sense? Okay. All right. So now what does this then do? It brings us to the following question. Supposing I tell you I have a graph which has linear number of vertices and quadratic number of edges. Does it mean it has a cubic number of triangles? Of course, no. Because as I said, you can take a complete graph which has quadratic, it has n square over 4 edges. It doesn't even have one triangle. It has 0 triangles. So asking for this statement, just knowing the number of vertices and number of edges, does not allow you to conclude any such thing. Okay. So your question then you have to ask yourself is, are there at all any graphs with these sorts of properties? That the number of vertices is linear in N and the number of edges is quadratic in N, and somehow the number of edges, triangles is cubic in N. Now remember, if you can show that the number of triangles is cubic in N, we are already done. Why so? Because remember, the number of useless triangles was at most epsilon n square. Correct? So if you have a cubic number of triangles, which means it could be some delta n cube triangles, but delta n cube will be more than epsilon n square as n becomes large. Yeah? So if you have cubic number of triangles, then Roth's theorem you have already proved. Does this make sense?
Yes, sir.
Yes, sir.
Yeah. All right. So you see, it basically boils down to this. We cooked up some graph in some way, some natural way in some sense. If you know only the following thing. You know the number of vertices is linear in N, number of edges is quadratic in N. Somehow you want to be able to show that the number of triangles is cubic in N. But that statement is plainly not true. It's not true about all graphs. So there must be something special about this. So now one way to try to answer this question then is to ask the following question. Are there any graphs with the following property, that number of vertices is linear, number of edges is quadratic, number of triangles is cubic? Of course, for the complete graph, it is true. It is if all edges are there, it is true, but something more general than that. So which graphs have these two properties? That is, if you have number of vertices, when I write G sub n, that means number of vertices is n. And it has quadratic number of edges. Yeah.
The triangles that we are counting, should the vertices be ordered tuples, or it is an unordered tuple, like for the triangles counting?
See, in the graph that we have created, the triangles, of course, will come one vertex in the set X, one in the set Y, one in the set Z. So
okay, so they should be ordered.
Yeah, but see, it doesn't really matter, because even if you take from unordered to ordered, see, any unordered triangle will give you 6 ordered triangles.
Yeah.
So if your number of triangles is cubic, how does it matter whether it is unordered or ordered?
Okay, just a constant.
It will only go by a constant factor, exactly. But good question. Any other questions? All right. Now, ask this question: which graphs on, say, linear number of vertices, on n vertices and quadratic number of edges have cubic number of triangles? Now, it turns out that this is, by now, it was a well-studied family of graphs. These are what are called the random graphs. Now, first of all, I have to make one very important disclaimer here. I have to make this point very, very clear. When we say random graph is not a graph. It is a distribution on graphs. So first, let me ask you guys one question. are all of you somewhat familiar with probability theory? Okay, so some of you have seen some things about probability. So one of the main things you know is probability. When you have a probability, you have basically a distribution. Now, the idea to think about for random graphs, the best is this model of what is called the Erdős-Rényi graph, which is denoted G and P. And what exactly is this G and P? Well, you think of n vertices. Now you imagine, that you have a coin whose probability of coming head is P. And for each pair of vertices, you toss that coin. If you get head, then say head comes with probability P. So then you keep the edge. If you get tail, you don't keep the edge. And you do this independent coin tosses for each of the pairs. Okay. So when I say G and P is not a graph, is actually a distribution on graphs. Okay. So you can only say, okay, what is the probability of picking a particular graph and so on. Now, I won't tell you this, but this is again a somewhat straightforward calculation. The number of, maybe this calculation I will show you because it's definitely worth seeing it once. What exactly is the count for the expected number of triangles? So supposing you pick some x, y, and z in the vertex set. What is the probability that this triple is a triangle? This must be an edge that has probability P. This edge probability P, this edge probability P. These three are independent. So probability that all three edges are present is P cube. The number of such triples is n choose 3. So the expected number of triangles is n choose 3 P cube, which is basically something like n P cube over 6. I know it's not exactly np cube, it's n minus 1, n minus 2, but for n large, n minus 1, n minus 2, and n cube are roughly the same order, so I won't make much distinction there. So the expected number of triangles is something like this. And interestingly, what is also true is that you can show that with high probability, the graph actually will have cubic number of triangles. So when I say a prominent family is random graphs, it's not exactly about a graph. It just means that if you randomly picked a graph in this manner, the probability that it will have a cubic number of edges will be very high. Does it make sense? All right. Okay. Now yes. Any questions? All right. Okay, good. So, but here is the problem. You see, a random graph ultimately, as I said, is not a graph. You want to talk about graphs that have this property. So one of the things you can ask is, okay, what if it is a graph that behaves like a random graph? Now, what do you understand by the term behaves like? In some sense, it must look like random. So for example, I mean, this is the way we talk. No, I'll draw, supposing I just take I could have done something like I picked say 4 or 5 vertices, and I just do it as the description I gave earlier. I'll just tell you the same thing, which is I'll just pick some 3 or 4 vertices. I'll just toss a coin and then I'll put an edge. Of course, the pattern of edges looks completely very random, like so you would say the graph is like a random graph. So you want to make this idea of what is random like a little more precise. So the technical term for is what is called pseudo-random. So your graph is called pseudo-random if in some sense it has random-like behavior, random-like properties. Now, what exactly are random-like properties? You can say, well, properties that the random graph had, if this graph has those kinds of properties, then it must. So for example, you take any 2 subsets, the number of edges between the 2 subsets, oops, All right. So you ask the following question. Well, if the number of, take any two subsets, the number of edges between those two subsets. See, again, in expectation, if the graph is like random coming from G and P, take two sets X and Y. How many edges are, how many possible pair? Well, the number of pairs of vertices from X and Y is size of X times size of Y. Each of these is an edge with probability P. So the expected number of edges is P times size X times size Y. So if the actual number of edges is approximately the expected number, then you would say that the graph has random like behavior. Now, another thing that you can do is, okay, you start with a fixed graph H, and supposing it's a triangle. One of the things you can do is an expected number of triangles would be something like P times the number of H times n to the power, the P to the power number of edges times n to the power number of vertices. That would be the expected number of labeled copies of any H in a random graph. Does this make sense? We see this is a somewhat technical point. Even if the things that I say later, I don't show you the proofs. It is very important that you understand these statements, at least in principle, for us to be able to move on. So, any questions?
No, sir.
All right. So what we will do is we will use this as our working definition for what is random like. And so for defining a pseudo-random graph, really, you need to be able to capture this parameter P effectively and efficiently. And so what you do is the following. For a pair of sets A and B, you define the density of the pair to be the number of edges between A and B. This is the number of EAB, stands for the number of edges between A and B, divided by the total number of pairs. So you see, if you picked edges at random, this EAB divided by size AB, size of A times size of B will be the probability that a randomly chosen pair actually are an edge. Does that make sense?
Yes, sir. Yes, sir.
Okay. Now, so based on this, here is the first definition of what is first technical definition we will make. You think of epsilon as a small fixed number. Typically, think of epsilon as less than 1/4. The 1/4 is a technicality, but you will understand the strength of the theorem only will make sense when epsilon is small. So you say a pair is epsilon regular if whenever you take any subset X in A and any subset Y in B, the number of edges or the density of the pair XY and the density of the pair AB must be roughly the same, which means to say up to an error of epsilon, they must be approximately the same. Does that make sense?
Yeah.
Of course, you can. There's one small thing here. Why do you need this extra condition? Size of X is at least this much, size of Y is at least that much. See, the problem is if supposing X were a singleton. If X were a singleton, then you see the problem is density of X and supposing X and Y are both singletons. Density of X or X comma Y will either be 0 or 1. So if the density of AB is somewhere between, if it is say half, this will make no sense. See, if the sampling becomes smaller and smaller, random nature of whatever choices you're making cannot be measured at all. Right? See, think of it like this. If I toss a coin only once, you have no idea of telling whether the coin was a biased coin or not. It's only when you toss it multiple number of times that you have access to its entire range of randomness. So in the same sense, this property must be true for sets X and Y that are not too small. And to measure what is not too small, you just keep these two things. That's all. Okay. So that a pair is said to be epsilon regular if you take any sufficiently large subsets X and Y of A and B respectively, the density of the pair XY and the density of the original pair A comma B are close to each other. They are within epsilon of each other. Okay. All right.
Are we using the same epsilon here, or is it just?
Yeah. So this is not a typo. It is the same epsilon. Now you can ask, why do you need the same epsilon? Now, if you don't put same, there's some other thing you can do. You can decide to keep an eta or a delta here, and then you will talk about epsilon, comma, delta regularity. But to keep things simple, I'm going to keep the same epsilon.
Okay.
All right. Okay. Now, here comes the first thing. Okay, supposing I have three disjoint pairs. See, in some sense, what I'm trying to do is, this notion of epsilon regularity is trying to be a proxy for the word random like. Random like, the notion of random like must somehow be captured. See, this epsilon regularity has nothing random about it. It is purely deterministic. But we are somehow trying to say that epsilon regularity must capture the notion. We have a question. What is the significance of epsilon in the previous slide? Can you repeat? Now, okay, let's go back. You see, here is the first point. Even in the random case, when you take a random graph, the number of triangles and so on, in expectation, it is this much. See, as I said, if you go back to the previous slide, there is this word of, I'm saying there is this thing about approximation. You see, the word approximate is used in all these cases. Right? I'm saying approximate. It's because, you see, in expectation it is this, but it is not going to be exactly equal. So when you say approximation, you need some idea of, you need some small wiggle room to move around the exact number. Which is why what we want to say is, if you pick a pair xy, the density of this pair need not exactly be this. It must be approximately this. When I say approximately, automatically, if you're thinking in terms of calculus, it means up to some epsilon error, they must be the same. Does that make sense?
So
Yes,
I
sir.
have another question.
Yeah, what?
So if we had we fixed it to be the subsets of A and B to be greater than at least epsilon times the bigger sets size of the, but it's for says that d of xy is non-trivial, like zero. It must not be 0 and 1.
Correct.
But for the case, let's say the original graph that we are trying to mimic using the pseudo random graph was a bipartite one.
Yes.
So then this DAP, the density of the pair, should be either 0 or 1, because either it is an edge between the either the two pairs of sets that are there, that are in the two bipartite sets, or it is in the same partition.
Okay. All right. See, first, two things. The setup of the original problem was to basically say that, you see, we wanted a result that says something like, okay, if we created some particular graph which had linear number of vertices, quadratic number of edges, and hopefully it has cubic number of triangles. Okay. Now, I am moving to something totally different. I am asking, okay, is there any general scenario under which you can say such things in the first place? So,
like, we are assuming that
so forget the original graph that I created, that the one with that x, y, z with the arithmetic progressions. Keep that aside. Now I'm talking about some statement about general graphs. I said random graphs have this very nice property that, you see, the number of triangles is cubic in the number of vertices. No problem. So I'm asking the same question, saying, okay, do random like graphs also have the same property? Now, when I say such a statement, I should also tell you what is the precise meaning of random like. Because if you don't have a meaning of random like, all these we are talking is just talking in the air. So in order to be able to define what random like is, we are trying to capture the idea of random like using the notion of epsilon regularity. Now, second point, some of you can ask, what if size of epsilon A is less than 1? Then, you can't do anything. See, if that is the case, then AB epsilon regularity will not arise. See again?
Yeah.
In such cases, we won't talk about the regularity when the things are too small. That's all. At the moment, at the moment we are just thinking very freewheelingly. So don't worry about all these edge cases where something is very small, something. Assume all those nasty things don't happen. Because what we're trying to build now is a theoretical foundation.
Yes.
All right?
Yes.
Okay. Now, let's go back to this question. So supposing I have three sets A, B, and C. And supposing size of A, size of B, size of C is all equal to M. And suppose AB, BC, AC are all epsilon regular pairs. Now, remember, I am using the word epsilon regular pair as a proxy to say random like. This is like saying they are almost as if random. Yeah. So if we have already seen that if it is random, the expected number of triangles must be cubic and all that stuff. Now I'm asking, supposing I work with this idea of epsilon regularity as a proxy for random. Is the statement still true? So I'm going to make some simplifying assumptions. Let me make this assumption that the densities of the pairs AB, BC, and AC are all at least D. Now, here's the question. In such a case, how many triangles are there? Are we guaranteed there's at least one triangle? In this case, do we know that there are cubically many triangles? See, if in this case, there are not cubically many triangles, cubic number of triangles, whatever we are doing is pointless. It's not going to capture what we are trying to achieve. Does it make sense?
Yes, sir.
All right. So, here is the first thing. As I said, the notion of pseudo-randomness must capture random-like behavior. So, if this pseudo-randomness, if I know epsilon regularity is there, I must somehow be able to say that the number of triangles is up to some constant d cube times m cube. Why d cube? Think of d as the probability of an edge between a vertex between A and B. D is also, well, D is at least, these are like probabilities. So there must be the probability of an edge between A and B is like D. An edge between B and C is D. Between A and C is also D. So the expected number of triangles will be d cube m cube because A, B, C are sets of size n. So in this setup, the expected number of triangles is d cube m cube. So you want to say the number of triangles must be at least of the order. This squiggle means this symbol that I have here is a shorthand for saying approximately of the order, up to constants. Okay. All right. So then let me show you this calculation. If I'm sort of running dangerously low on time, which is I'm not very close to finishing, but let me try to show this. So let me go to this picture. Let me make this picture here. I have a set. So I have these three sets A, B, and C. Okay. And what I want to do first, see, I want to somehow show that there are many, many triangles between these three sets. What am I trying to do now? I want to first consider this set. Okay. So this is unfortunately I have not the laptop, the tablet device is heating up so much that its latency for my drawing and then showing up on the board is showing up simultaneously is causing a problem, bigger problem than I anticipated. Anyway, I'll try to see if this still works. See, so I have my three sets. See if this works. Yeah. This is A, this is B, and this is C. Now let's look at what this XB star is. XB star is all those vertices here. Okay. Whose degree into B is small. You see, we are saying that the density between these two pairs is D. Density is at least D. Okay. We are told that all three pairs, AB, BC, AC, are epsilon regular. Right? Which means, you remember the definition of epsilon regular I told earlier. XB star is those vertices whose degree into B is somewhat small. Similarly, you define what is XC star, whose degree into this is somewhat small. Okay. So the main point is that I want to claim is that if XB star is large, I want to say that XB star must be a small set. Why is that? See, I want to say that XB star, supposing X size of XB star were at least epsilon times size of A. Okay, then note the following. The number of, you take the density between the pairs XB star and B. What is this? This is the number of edges between these two divided by their sizes. By definition. Now, by the definition of XB star, the numerator is less than, well, for each vertex here, the numerator is at most this. And the denominator remains this, which means this is less than D minus epsilon. Correct? Are you following me?
Yes, sir. Yes, sir.
Now, do you see a contradiction? I've calculated the density of this pair. I'm saying it must be less than D minus epsilon. But I'm assuming that A and B is an epsilon regular pair. Which means, see, if XB star were a large enough set, then the density of these two pairs and the density of AB must be at most epsilon. That is what epsilon regularity means. Now, this fellow is at least D. So, this guy must be at least greater than or equal D minus epsilon. No. Otherwise, this inequality will not happen. But on the other hand, we are saying that this then will be strictly less than D minus epsilon. Okay? Does it make sense?
Yes, sir. Yes.
So what does that show you? It shows that this cannot happen. This must be small. Similarly, XC star must be a small set. So as I said, if XB star is at least epsilon A, then this must be less. So that's not possible. So size of XB star is less than epsilon A. Similarly, size of XC star is less than epsilon A. And so the main point is then you take any X in, you throw away these two small sets, right? Once you throw away these two small sets, take any of the remaining vertices. Every edge between these two neighbors along with that vertex of X will give you a triangle that contains X. Does that make sense?
Yes, sir. Yes.
So how many triangles does that count? Let's just do this very simple calculation. At least I hope to do all these so that before whether we can finally prove what we want or not, I want to count number of triangles, right? Now, how do I count the number of triangles? Let's do this. The size of this part, once I throw away this, each of these two sets is at most size epsilon A. Size of A is M. So size of X is at least 1 minus 2 epsilon times z. Correct? Yeah. And so, and now you pick how, so once you pick a vertex in X, it has at least d minus epsilon m neighbors in B and d minus epsilon m neighbors in C. You pick those two, or you take the set of those neighbors. Now between them, because these two must be also dense sets, the epsilon regularity of the pair BC will tell you that there are at least d minus epsilon n, the size of these two set squares, many edges. So it's a simple calculation. I'm not doing it now for lack of time. But if it's a fairly straightforward calculation by which you can conclude that the number of triangles must be this. See, so only thing you need here is d must be at least 2 epsilon. Otherwise, this will, I mean, if d is not 2 epsilon, this may become very, very small, and then it doesn't tell you anything. But what it then tells you is that the number of triangles indeed becomes cubic in the size of M. So more so, the same argument shows that if the densities are some DAB, DBC, and DAC, the number of such triangles will be this number that you have in the bottom. Does it make sense?
For here, D should be greater than epsilon for our case.
See,
Otherwise,
I'm saying, yeah, of course it should be. In fact, I'm writing greater than 2 epsilon. See, think of it this way.
only like why 2 epsilon exactly?
Oh, okay. See, if you don't keep a gap here, then this term may be way too small. See, you put 2 epsilon, then d minus epsilon is at least epsilon. So this other factor that you have here depends only on epsilon. See, if d minus epsilon is very, very small, you know, it's like d is epsilon plus 1 by m. Then d minus epsilon will be that 1 by m will cancel, so you won't get anything.
Okay.
You understand what I'm saying? See,
Yeah,
it
it
is
shouldn't
not
be very small so that.
Yeah, it shouldn't be so small that m cube doesn't matter.
Yeah.
Okay, good. Now, so here is a combinatorial approach to Rod's theorem. I don't know how much. See, the time is almost 1. I probably will go on for another 10 minutes. But after that, you know, I'll probably be eating into your lunchtime as well. So I won't try to go too much into it. So let me try to give you a basic outline of what we are trying to do. So to prove Rod's theorem, if we can show that in our constructed graphs, remember the graph that we had x, y, and z. Supposing all the pairs of sets x, y, y, z, and zx are all epsilon star regular for some small epsilon star, then we are done. Correct?
Yes, sir.
Right. Now, it's interesting. So you don't even, now that may not be possible to do, but then here's a simpler observation. You don't even need the epsilon regularity of the triple x, y, y, z, and x, z. Even if you had it for some subsets of large enough size, that also will suffice. See, imagine you had a set A of x, B of y, and C of z, where size of A is at least 1/10 size of x. Size of B is at least 1/10 size of y. Size of C is at least 1/10 the size of z. You're still done, right? Because the number of triangles will fall by a constant factor, but it will still be cubic in the total sizes. But here comes the problem. How do you even accomplish this much simpler objective? Now, I had originally hoped, as I said, my original hope was to try to show you a complete arrival, complete natural way to arrive at the statement itself. But what I will do now is I will skip forward. I will cut to the chase and tell you that this is something that comes as a consequence of the regularity lemma. So rather than tell you everything, I will tell you what the regularity lemma's statement is. So here is a definition. You start with a partition of the vertex set. into say almost equal parts. Actually, the almost equal is not really necessary, but yeah, just keep it. You partition the set into almost equal parts. What do I mean by almost equal? Well, if K does not divide the number of vertices, then some parts will have, you can't have all of them having the same number of vertices, right? So you say that the partition is epsilon regular if many pairs are epsilon regular. So to be more precise, the definition of epsilon regularity, I have some things over here, but I'm going to come to the precise definition here. Supposing you have a partition V1, V2, Vk, where each of them have size C, and we call a partition V1, V2, Vk as an epsilon eta regular pair, or think of eta as epsilon itself. If the number of irregular pairs, what do I mean by an irregular pair? An irregular pair is a pair that is not epsilon regular. Okay? If the number of irregular pairs is at most epsilon, so think at the moment I put an eta, but think of eta as epsilon itself. So you say a partition into k parts is a regular partition if the number of irregular pairs is at most epsilon k square, where k is the number of parts. Okay, I've skipped a few slides, but what those content are has nothing to do with what I'm saying right now. And at this point, I want to tell you the main statement of the regularity lemma, because at least that much, if not anything else, you should be able to take this statement back with you. Given any epsilon, there exists an M such that the following holds. Any graph has an epsilon regular partition. In other words, with at most M parts. What this means is, given any graph, there is a constant M which depends only on epsilon. And supposing you're given an epsilon, there is a constant M that depends only on epsilon, such that the vertex set of the graph can be partitioned into M parts, where M depends only on epsilon, really, such that most of these pairs are epsilon regular pairs. What do I mean by most? The number of pairs that are not epsilon regular is at most epsilon times epsilon k square, where k is epsilon m square. That's the point. I realize I might be saying too many things here, and I'm probably making it a little confusing, but I just want to pause at this moment and say, do you understand the statement of the theorem that I just stated?
Yes, sir. Yes.
Okay. Now, what is the statement then? Any graph, if I tell you an epsilon, there is a bounded number of parts. That bound depends only on epsilon. It does not depend. This is the most, of course, there is something about the proof. I'm skipping through this because I have not told you the proof. But the more important thing is, the punchline of the lemma is the following. The number of parts in the partition does not depend on the number of vertices of the graph. So think of it this way, because this is, I'm going to cut the graph into some number of pieces. The number of pieces here depends only on epsilon. It does not depend on the number of edges, number of vertices of the graph. Most of these pairs are epsilon regular pairs. Now, this is true for any graph. For all graphs, the following statement is true. So let's go back to the statement of the regularity lemma. For given an epsilon, there exists an M epsilon such that the following holds. Any graph admits a partition. It does not depend on how many vertices are there in the graph. It does not depend on the graph. Of course, the number of parts in the graph will depend on the graph, but the more important thing is that that number M does not depend on the graph. It's like saying any graph can be cut into 1,000 pieces, where, so at least 900 pairs of these pieces are regular. Now that is a very deep statement, because it is a statement about all graphs, and it is not at all clear that such a thing must trivially be true. As I said, statements about all graphs are usually trivial, or they are highly non-trivial. Now, at this point, let me make this digressive note. At least this is something that most of you probably have seen. All of you are familiar with what are exit polls?
Yes, sir. Yes, sir.
You've heard of exit polls. What exactly are exit polls? Recently, there have been elections everywhere, and then there were exit polls, and then a lot of tamasha about whether the exit polls were correct or not.
Yeah.
Now, an exit poll is a poll that is taken after the election is over. That is, after people have voted. See, polls before, they ask people whom they will vote for. Problem is, people can say, you know, I may vote for this, I may vote for that party, it doesn't matter. But the point about an exit poll is that, and again, you assume that people are probably not telling you lies. Of course, there are statistical methods to account for people possibly telling lies, or how to make them tell the truth, even though the surveyor himself may not know whether they are telling what they are answering. There are sophisticated statistical techniques for all this. That's not my point. But the point is, and this is something that you will hear in many of these TV debates, especially coming from the losing party people who have lost, whom the exit polls predict they will lose. Typically, they make these following statements. How can, see, the exit poll surveyed around 5,000 people, but the state of Tamil Nadu has 6 crore people. How can, just sampling 5,000 people accurately represent 6 crore people? So this is all wrong and all that stuff. Usually people who make such statements are totally ignorant about statistics and probability, or they know, which means they are liars. The important point is, when you make an exit poll, how many people are polled there does not depend on the size of the underlying population. It only depends on how much of margin of error you are ready to tolerate. Now, I put this point because, you see, the statement of the regularity lemma has some similarity with this. The number of pieces into which the graph vertex set is cut, it depends only on the amount of error of your regularity partition that you are ready to tolerate. It does not depend on the number of vertices of the graph. Okay, so this sort of statement is not completely, that's why I said a digressive and yet not entirely digressive. There is a similarity in both these things, but since I could not tell you the proof in much greater detail, I'm afraid I'll have to leave it to this. But I will share these slides, and Shubhajit can probably forward it to those of you who are interested, and so on and so forth. So there are other points. You see, why do we insist on a small number of pairs? This is actually a more technical point. That what it allows you to do is, you can basically remove a very small number of edges from the graph and get a residual graph which looks like all its pairs look like random pairs. So in some sense, this is saying that every graph, especially when the graph is dense, consists of a bounded number of random pairs of graphs. Now, that is a very deep philosophical statement. I mean, there is no reason why that should have been true. It just happens to be true. So, since unfortunately I could not tell you more about the proof, I will at this point wind up my talk, and I thank you for your attention and for being here, patiently listening to what I have to say. If you have any questions, I can take them now. But yeah, I'm done. See, you must understand that since we are working on budgeted time, even though I had desired to show more in the slides, how to contact me? See, at least for the slides, I will pass them on to Shubhajit, and he can probably either mail you a copy, or he can even maybe take a printout and distribute or something. Since all of you probably have
Yes, sir. Yes,
that should be some way of dealing with that. That's not a problem. Okay, but yeah, so the more important thing is, you see, one important punchline that you should take from here is that there are many. Why are you interested in looking at random objects, like a random graph and this and so on? Random objects have some very nice things about them, that is, even if you can't specifically tell structural things, statistical things about random objects are usually very robust. Like, for example, going back to the exit poll, when you randomly sample if I pick a person at random, I cannot tell whom they voted for. But if I randomly pick 1,000 people and know whom, if I take the proportion of whom they voted, right? Or if I pick a random person and ask that person's vote, whom they voted for, that doesn't tell me any information on who's going to win the election. But if I randomly pick some 1,000 people, it will actually give you a very good estimate on who is probably going to win the election. Right? So in that sense, randomness has a power, especially when you're doing cumulative statistics. And that idea, that philosophical idea, can be exploited very, very beautifully, even to solve mathematical or absolute questions that have nothing to do with randomness. That is the more important takeaway lesson. And if I've managed to communicate a little bit of that to you, I think I've done reasonably. But even if you didn't understand some things in the talk, it's fine. Some of these things may take more time. Hopefully, when you read or go through the slides, it may help you a little more. So, yeah.
Sir, is the proof only just existential, or the constructive proof is also there for the regularity lemma?
Okay, so that's a good question. So what you can do, the proof can be algorithmized. But there is something interesting about this. See, if I give you a graph and a partition, and I ask you, is this a regular partition? That is not easy to verify.
Yeah, because I have to check a large number of.
You have to count. You have to
vertices
check
and
exponentially many checks.
Yeah.
So a given partition, whether it is an epsilon regular partition, is not easy to verify. However, if I just give you a graph and ask you for a partition, to get an epsilon regular partition, that you can do in polynomial time.
Oh, okay.
Yeah. Yes.
So if anyone has any other question.
Yeah. So Swayanshu has asked, so regularity, every graph vertices can be partitioned into m epsilon, not into m epsilon, into at most n epsilon, but sure, where every part of vertices is random, like not every, most. See, there is something that there is some precise nature in these statements. Remember, anytime you make a statement with random like objects, you will always make only approximate statements. Making exact statements will not be possible. So, to Swayanshu's remark in the messages, not every pair, most parts are random like. That's the most correct statement. Okay? Yeah. All right. Any other questions? Okay, if there are no other questions, so when is this? This is part of the cap that you have for limit, right?
Yes, sir. Yes, sir.
When is the date of the exam?
We concluded the exams.
It's already done.
So
it's already done.
Yeah.
Okay, all right. So anyway, so whether you score well in this particular exam or not, and whether you see, there's one thing that I have about a general comment I will make about examinations and these sort of competitive types of exams and so on. Yes, they do measure something. They do kind of measure how serious you are about something, and if you do well in it, it usually has good correlation with your being able to do things in the future. But, all important but, it's neither necessary nor sufficient. to be able to do anything well, and this doesn't even have to do whether it is in mathematics, you don't have to necessarily be good in timed clock. Time can be 3 hours, 3 days, it doesn't matter. If sticking to just the topic of doing mathematics, I suppose, my larger point here would be that if you want to pursue something, do it seriously. Don't do it frivolously. That's the more important thing. It's very easy to start and after a month or two lose interest and fizzle away. Now, if you do that consistently over many, many things, you will become a jack of all trades and master of none. Okay, and in the current day and so on, with AI tools becoming extremely powerful, if your expertise doesn't extend beyond what a machine can do, then you are not going to be considered necessary, because a machine can do whatever you can do. So in order to acquire expertise in anything, I'm not saying mathematics in general, it can be whatever area of pursuit you're interested in. You have to give enough time to master certain things. That time you give, it can be a year, it can be 2 years, 5 years, it can even be a decade, but you have to put in that time. You do that, slowly the effect will start to show on you. That's my general bit of advice to you. See, most of you are still very young guys, and your interests are likely going to change within the next 4 or 5 years. So even if you don't end up doing mathematics, there's nothing wrong in it. There may be some people who say mathematics nahi kar rahe, to kya kar rahe ho? All rubbish. You can do whatever catches your interest, but do that sincerely. Do it honestly. Okay, with that little word of advice, I think I will stop my lecture here. All right, so all the best to you guys in whatever you're going to do in your future, and take care. All right.
Thank you, sir. Thank you for the talk.